Yeah, welcome. So we are discussing about instruction hazards. So the topic we'll be discussing in this lecture is branch prediction. So to give a brief overview about where we are currently, basically we are discussing about the concepts of reducing branch penalty. We are discussing the techniques to reduce the branch penalty. What is branch penalty? The delay or the stall that was created in the pipeline because of a branch instruction, that is called as branch penalty, and we are discussing the methods to reduce the branch penalty. In case of unconditional branch instruction, the branch penalty can be reduced by using sophisticated fetch units, which can by using sophisticated fetch unit, the branch target address can be calculated immediately after the decode stage. Otherwise, the branch target address can be calculated only after the execution stage. But by using sophisticated fetch unit, branch target address can be calculated immediately after the decode stage. So this is one technique to reduce the branch penalty for unconditional branch instructions, which we have discussed in the last session. Coming to conditional branch instructions, there is a way to reduce the branch penalty, and that is by using delayed branch. This also we have discussed. With delayed branch, what happens in the sense, the instruction that follows the branch instruction, the compiler will reorder the instructions in such a way that the instruction that follows the branch instruction will always be executed. So this can be done by an optimized compiler. It may not be always possible, but wherever possible, the compiler should ensure that the instruction that follows the branch instruction should be executed. By that, what happens in the sense, you need not ignore the instruction that follows the branch instruction, even in spite of whether the branch is taken or not taken. So that concept is called as delayed branch. So that is also one method of reducing the branch penalty. But delayed branch is applicable for conditional branch instructions. Okay. Similarly, there is another method to reduce the branch penalty for conditional branch instructions, and this method is called as branch prediction. Branch prediction is also one of the technique to reduce the branch penalty for conditional branches. So this branch prediction can be further classified into two types. One is called as static branch prediction. The other one is called as dynamic branch prediction. So this is what we are going to discuss in today's lecture. So in today's lecture, we are going to discuss about branch prediction techniques, which is basically of two types. One is static branch prediction, the other one is dynamic branch prediction. So all these branch prediction, all these things comes under the main heading of reducing branch penalty. And again, reducing branch penalty, we are discussing under two headings: how branch penalty should be reduced for unconditional branch instruction and for conditional branch instruction. For unconditional branch instruction, to reduce the branch penalty, we have one technique, that is by using sophisticated fetch unit. The branch target address can be calculated immediately after the decode stage. There is also another method in unconditional branch instruction, by that also you can reduce the branch penalty, that is by instruction by using a instruction queue. And the fetch unit will prefetch the instruction and fill the instruction queue. Okay, so this is also one of the technique. Okay, actually this second technique is applicable for everything, not only for unconditional branch, it is applicable for all branch instructions. Coming for conditional branch instruction, to reduce the branch penalty, the first method we have is delayed branch, by which we ensure that the instruction that follows the branch instruction will be always executed. And the next method is branch prediction, which is what we are going to discuss in this lecture. It is of two types. One is static branch prediction, the other one is dynamic branch prediction. Okay. So with this introduction, let us get into it. Right. So basically, branch prediction is a technique to reduce the branch penalty. So it is a technique to reduce the branch penalty. Right. Yeah. So basically, it is a technique to reduce the branch penalty. It is one of the technique to reduce the branch penalty. So as the name says, here we are going to predict. It's just an assumption, nothing more than that. We are not going to do anything systematically. It is just a predict. It is just we are going to predict that whether the branch will be taken or not taken. Right? But slowly we will be formalizing that method of predicting. Will be formalizing that method of predicting. That's what we are going to discuss here. So this branch prediction technique can be classified into two headings. One is called as static branch prediction. The other one is called as dynamic branch prediction. So first let us talk about static branch prediction. With static branch prediction, what we will do in the sense, assume that we are talking about conditional branch. So it means the branch can be either taken or not taken. Depends on several situations. Depends on whatever the situation prevails. Okay. So it is a random branch instruction. Like it can be either taken or it may not be taken. So what we can assume in the sense, we can assume that always the branch will not be taken. Like that we can assume. That is one of the option. You can assume that always you assume that the branch will not be taken. So for example, if there is a branch instruction something like this, branch, if there is a branch instruction, branch, if something is equal to something, say x less than 10, then go to some address, say branch x less than 10 to say some address 1000. So if x is less than 10, it should go to 1000. Maybe 1000 is somewhere here. The address 1000 may be somewhere here. It is here. Okay. If it is not less than, if x is not less than 10, if x is greater than 10, then these instructions should execute. Now, the static branch prediction, what it says in the sense, always assume that either branch will be taken or it will not be taken, like that every time. So let us assume that we are always assuming that the branch will not be taken. So let us assume always we are assuming that the branch is not taken. I am calling it as NT. NT means branch not taken, or we can call it as BNT. BNT means branch is not taken. So when this instruction executes now, we let us assume whatever may be the x, we always assume branch is not taken. So this instruction will be fetched. But later, after few clock cycles, we come to realize that whatever we assumed it is wrong, then we have to discard this instruction. Okay. If the assumption is right, that whatever we assumed that branch not taken, it is correct, then this instruction fetch will not go waste. So basically this idea it is based on what principle, in the sense, for a random branch instruction, 50% of the time the branch will be taken generally, and 50% of the time the branch will not be taken. So branch taken probability is 50% or 0.5, and for a random branch instruction, and the number of times the branch will not be taken, branch not taken, that is also 50%. So that this algorithm says always you assume either the branch is taken or is not taken and proceed. And suppose if the assumption is wrong, then whatever the instruction which was fetched because of that, those instructions should be discarded. But here one more thing we should keep in mind, that is we are assuming, in this case we are assuming that the branch is not taken. We are assuming that the branch is not taken, and we are assuming that the branch is not taken, and we are fetching these instructions, the following instructions. But after certain clock cycles, when this instruction is actually evaluated, say if x is 5, if x is 5, then our assumption is wrong, because we assumed that branch will not be taken. But if x is less than 5, then the branch should be taken. Then these instructions, whatever we have fetched, they are not correct. They should be discarded. They should be discarded. So when you execute such instructions, that is when you fetch or execute such instructions based on prediction, these instructions, the processor should ensure that these instructions should not update the registers or memory locations. They should not update the registers or memory locations. That is, registers or memory locations should not be updated. Even if there is a need, it should not update. It should store the result, whatever the result coming out of this instruction, it should be stored somewhere temporarily. But registers and memory should not be updated. Because if registers and memory are updated, then again when you want to discard these instructions, again those updated values should be again brought back to their old values. Okay, so all these are unnecessary overheads. Okay, to avoid that, what it is suggested in the sense, whenever some instructions were executed based on some prediction, so here we are predicting that the branch will not be taken, so we are executing these instructions, but we don't know whether really it will be taken or not. So when you say assume two instructions are executed, assuming that the branch will not be taken, so these two instructions it can execute, but it should not update any registers or any memory locations. This care should be taken. Okay, but later after the actual assessment is done, whether the branch should be taken or not, after that, if our prediction is correct, that is initially we predicted branch will not be taken. If our prediction is right, then after that this content can be returned into the register or memory. If our prediction is wrong, we will discard this instruction. So anyway, it has not updated the registers or the memory. So this is the idea of static branch prediction. So with static branch prediction, we always assume that the branch is either taken or is not taken. Okay. So whatever we have discussed about static branch, that was explained here. It is the simplest form of branch prediction. So static branch is the simplest form of branch prediction. It assumes that the branch, so normally it assumes that the branch will not be taken. You can assume either way, but generally the static branch prediction assumes that, always it assumes that the branch will not be taken, and it will fetch the next instruction in the sequential order. If the branch is not taken, what will happen? The next instruction will be taken and it will be executed. So here we assume that the branch will not be taken, so it will fetch the next instruction and it will start processing sequentially. If the prediction is correct, the fetched instruction is allowed to complete and there is no penalty. But if the prediction is wrong, if you have mispredicted, then there will be penalty. Then there will be, we have to pay the price. Okay. But it works on the principle like what? 50% of the time any branch will be taken and 50% it will not be taken generally, if it is a random branch instruction. Okay. So that's it about static branch instruction. Coming to dynamic static branch prediction. With dynamic branch prediction, here the processor will maintain something called as branch history. Processor will maintain something called as branch history. So based on the branch history, we are going to decide whether the branch will be taken or not taken. Here the processor will maintain something called as branch history, and based on this branch history, the processor will decide whether the branch will be taken or not taken. The simplest form of branch history is what, in the sense, very what you call very naive method or very simple form of branch history technique. What it says in the sense, if in the previous round, if the branch is taken, then in the next round also you assume that the branch will be taken. In the previous round, if the branch is not taken, then in the next round also we should assume that the branch will not be taken. If in the previous round, in the previous execution, whatever it may be. In the previous round, if the branch is taken, then next time when that particular branch you are about to execute, you should assume that the processor will assume that the branch will be taken. Suppose in the previous round, if the branch is not taken, then if the branch is not taken, then in the next round also the processor will assume that the branch will not, this is BNT, branch will not be taken. So based on this assumption, it will work. So initially it will have some assumption. Assume that initially the processor assumes that the branch will not be taken. Yeah, just a minute. Assume that initially the processor assumes that the branch will not be taken. Okay, so that is say in the previous round the branch is not taken, so the processor assumes that the branch will not be taken. So the processor assumes that the branch will not be taken. So the processor predicts that the branch is not taken. So the processor predicts that the branch is not taken. So you say the say this is the instruction I1, instruction 1. So instruction 1 is fetched, okay, it is decoded, it is executed, it is written. Say instruction 2, this is the branch instruction. Let us assume instruction 2 is the branch instruction. Here it is a conditional branch instruction. Now processor is assuming that the branch is not taken. So this is the actual branch instruction which is getting fetched and decoded. By the end of decode, we will be knowing whether the branch is taken or not taken really. This is just an assumption. As the processor is assuming that the branch is not taken, it will fetch the next instruction. I3 will be fetched. So here the processor assumed that the branch will not be taken. But assume that the result came here out of the branch instruction. The result that came out is branch should be taken. That is, you have to execute the instruction IK after this. Now the processor will drop this instruction and it will start executing IK. Now IK can be fetched at which clock cycle? It can be fetched at 5th clock cycle. Because only at the end of 4th clock cycle we know that I2, the result of I2 is branch should be taken. So in this round, what is branch taken? So next time when processor want to execute this instruction I2, next time processor will assume that the branch will be taken. So this is how this branch history works. That is, it will record the recent branch outcome. If the recent outcome is taken, then the next time when the branch is to be executed, it will assume that the branch will be taken. If the recent outcome is branch not taken, then next time when the branch is to be executed, it will assume that the branch will not be taken. Okay. So this is the basic idea of dynamic branch prediction, and some more thing we can understand from here. There are certain other things we can understand. One is that, say you assume the loop. In case of loop is also one form of branch. Take a for loop, for example. I'm talking about high level language, not in assembly language. We can connect it with assembly language also. Take a for loop. Inside a for loop there are 4 or 5 statements. So as long as the for loop is condition is true, the statements inside the for loop will execute. When the condition becomes false, of the for loop, the statement that follows the for loop will execute. So that is also one form of branch. Actually, there is a branch instruction only, but we are representing it as a different format, which is a loop or some other way. So in such cases, what should we predict? What is the wise way to predict? Say for example, there is a for loop which is something like this: for I is equal to 1 to 10. So inside this there are some 5 instructions are there. So as long as I is less than or equal to 10, these instructions will execute sequentially. But the moment I becomes 11 or if I is 0, then the control should go to this instruction. So let us assume these are some addresses, say x1, x2, x3, something. Okay, say the outside that address is say x10, x10. So this is also one form of branch. What type of branch? If I is between 1 to 10, execute x1. That is sequential execution. That this is a sequential execution. You need not tell anything to the processor, because normally processor will execute everything sequentially. So after this it will do this. Only if I is greater than 10 or if I is less than 10, then it is an instruction to the processor that go to x10. So this can also be, so the processor or the compiler will treat this instruction, we call it as for loop. But how the compiler will treat? Compiler will see it this way. If I less than 0 or I greater than 10, then compiler will what it will treat, go to x10. Compiler will see like this. So if this is the case, go to x10, like that only the compiler will see this instruction. So this is also one form of branch instruction. So in this case, what should we decide? In this case, what should we assume? What should we predict? We are discussing about branch prediction, dynamic branch prediction. Here, what should we predict? Should we predict the branch to be taken or not taken? What should we predict? Here, in this type of situations, we should always assume that, especially in case of for loop or while loop. In case of for loop or while loop, we should always assume that the branch will not be taken. In case of for loop or while loop, we should assume that always the branch will not be taken. Okay, or you can say B and T, branch not taken. Why? Because here you see, first time this for loop, say initially I is here, this itself is initializing I to 1 to 10. Okay, for I is equal to 1 to 10. So 10 times branch is not taken. For first 10 times branch is not taken. Am I correct? So branch not taken means the instruction that follows the branch is executing. Only once the branch is taken, at last I becomes 11. At last I becomes 11. At that time it checks I is not 10, so it will go to x10. Okay, so 10 times branch is not taken, only once the branch is taken. So in case of for loop or while loop, we should assume that branch will not be taken, so that the penalty will be less, so that our prediction will go wrong only once, and remaining all iterations of the loop, the prediction will be correct. If the for loop is executing for 1000 times, then our prediction will be right for 1000 times. Only the last one time the prediction will be wrong. So this is applicable for while loop also. This is applicable for while loop also. The same thing is applicable for while loop. You can work out on that. But let us assume the case of do while loop. Consider the case of do while loop. In do while loop, what should we always, what the compiler should predict? What is the wise way to predict? Should it always predict the branch will be taken or it will not be taken? In do while loop, the condition comes at last. In do while loop, the condition will come at last. And if the condition is true, the branch should be taken. If the condition is false, the branch will not be taken. So here what should we do? So let me write that. In case of do while loop, so do while loop is something like this. See here we are declaring I is equal to 0 outside the loop. Then do something is there, some instructions are there. So some 4 or 5 instructions are there. At last we say that while I less than or equal to 10, and say one of this instruction is I is equal to I plus 1. I is equal to I plus 1. So what it will happen, as long as I is less than 10, this loop should execute. So this is also a branch. This is also a branch instruction. What this branch instruction says say this starting address is 1000. Let us assume this starting address is 1000. Then this instruction, what it says in the sense, as long as I is less than or equal to 10, you go to which location? Go to 1000. So every time it will check if I is less than or equal to 10, then go to 1000. This is also a branch, conditional branch instruction based on this I. If I is less than or equal to 10, go to 1000. That is what it says. So here what should we assume? Here what the processor should assume? Should it always assume the branch to be taken or not taken? Here we should always assume the branch to be taken. Then only it is advantage for the processor. Because you see, 10 times the branch will be taken. When you start I with 0, 10 times the branch will be taken. Only the last one time the branch will not be taken. So here we should assume that the branch will be always taken. Then only we can take the advantage then only we can take the advantage and we can minimize the penalty. Our objective is to what? Reduce the penalty. That is the objective of the topic. Is it clear? So to generalize the thing, I gave the example of for loop, while loop and do while loop. But actually the textbook does not talk anything about for loop, while loop and do while loop. The textbook only says that if loop occurs at the beginning, that is, a loop can be written in two ways. In assembly language, loop can be written in two ways. That is, you can keep the branch instruction either at the end of the loop or you can keep the branch instruction at the beginning of the loop. Okay. You can keep the branch instruction at the end of the loop or you can keep the branch instruction at the beginning of the loop. If the branch instruction is at the beginning of the loop, then that is equivalent to a for loop or a while loop. If the branch instruction is at the end of the loop, then that is equivalent to a do while loop. So if the branch instruction is at the beginning of a loop, so loop is nothing but set of statements which is to be executed repeatedly. So if the branch instruction is at the beginning of the loop, something like this, say branch some condition, we are talking about assembly language now. Branch R1 not equal to or R1 not equal to 0 or R1 equal to 0, whatever it may be. Branch R1 not equal to 0 to some address. Otherwise, it will execute this instruction. Branch R1 not equal to 0, say out of loop, O loop, and say O loop. Okay, O loop is somewhere here. Okay, so it is here. Fine. And at last, say this is the loop, this is the set of instructions for loop. Here the last instruction, let us assume it is branch, not loop, it is branch loop. And what is loop? Say this is the label for loop. Now you see branch R1 not equal to 0. If R1 is not equal to 0, if R1 is not equal to 0, go to loop. Okay, otherwise execute this. So as long as R1 is not equal to 0, this thing will execute. Okay, say here at every time we decrement R1. Every time we inside the loop we decrement R1. Outside we set R1 as some value. Move R1 comma 10. So is R1 is 0? No. Now if it is not equal to 0, or say it is equal to 0, not equal to, I'm sorry, if it is equal to 0, so if R1 is equal to 0, come out of the loop. Is 10 is equal to 0? No. So this will execute. Then next time it will become 9. Is 9 is equal to 0? No. So this will execute. Is 8 is equal to, so like that it will execute. So basically this is equivalent to a for loop or a while loop. So in this case, always what should we assume? That is when the branch is coming at the beginning of a loop. This is the loop. And this is the branch. We are talking about conditional branch. Here also there is a branch, but this is an unconditional branch. Always it will jump to loop. But this is a conditional branch. when a conditional branch occurs at the beginning of a loop, then always assume that the branch will not be taken. Always predict that the branch will not be taken. But when a conditional branch occurs at the end of the loop, then always assume that the branch will be taken. Okay, because in end of the loop it will become something like a do while loop. In end of the loop it will become something like a do while loop. So these are different ways of writing loop. So if you want to write it in do while style, then it will be something like this. So now also here we'll have what now also here we'll have move, say move, this statement will be there as it is, move r1 comma 10. Then here we'll have loop colon, some instructions will be there, and then we will decrement r1 decrement r1 uh, now here what we will say, branch not equal to 0, branch not equal to 0, loop, that is, as long as r1 is not equal to 0, keep on repeat this. Finally when r1 becomes equal to 0, it will come out of the loop, right? So here what should we assume? Here always we should assume that the branch will be taken. Okay, but in this case we always assume that the branch will not be taken. So this is the difference, right? That is, for a loop, if the conditional branch instruction comes at the beginning, the processor should always predict that the branch not taken. And for a loop, if the conditional branch instruction comes at the end of the loop, then the processor will always assume that the branch will be taken. So then only it can take the advantage of that. Okay. So this is this is also one way of predicting branch. So previously we have discussed that bit prediction. I mean, using the history. We will be coming back to that. We will be discussing about the history in detail. But to that, I am adding these two things also. So dynamic branch prediction, it includes all these things. So first is, it works based on the recent history. Previously, if the branch is taken, it will assume in the next round also the branch will be taken. That is, it will predict in the next round also the branch will be taken. Previously, if the branch is not taken, in the next round also the processor will predict that the branch will not be taken. Apart from this, the processor can also apply these intelligence or these logics. That is, in case of a loop, if a branch instruction is coming at the beginning of a loop, then it should always predict that the branch will not be taken. Because in case of a loop, as long as the loop executes, if the branch instruction comes at the beginning, which is equivalent to a for or a while loop, then that instruction will fail only once. Similarly, in case of a loop instruction, if the branch comes at the end of the loop, then always we should assume that the branch is taken. Okay, because only at the last time the branch will not be taken. So this also, whenever the conditional branch instruction comes, processor should check all these things. So whatever we have discussed here is an example. Here is an example for the loop at the beginning. So loop, or we can say not branch at the beginning of the loop. Branch at the beginning of loop. Okay. So example, the high level language example is for loop and while loop. So whatever we have discussed, same. See, move r1 comma 10, branch r1 equal to 0 out of loop. If r1 is equal to 0, go out of loop. And these are the statements inside the loop. The last statement inside the loop is decrement r1 and branch loop. This is an unconditional branch. Whereas the top one is a conditional branch. This is an unconditional branch. Okay, so here always it will be predicted as branch not taken. Always it will be predicted as branch not taken. Okay. Instead of assume, let us use the word predict. Always it will be predicted as branch not taken. So this is an example of where the branch comes at the beginning of the loop. Similarly, branch can come at the end of the loop. So this is the example. So here also we are moving R1 comma 10 loop, and but at last at the last statement in the loop is decrement R1 and then branch R1 not equal to 0. If R1 is not equal to 0, loop. So here we most of the time we predict what? Not most of the time, always we predict that the branch is taken. Branch is taken. So only it will fail only once. And these are the statements outside of the loop, which we are not bothered. Okay, fine. So now let us go back to the previous thing where we have discussed about the branch prediction based on the recent history. So we have discussed that the branch prediction, the simplest form of branch prediction is to predict the branch based on the recent history. That is, in the previous execution, if the branch is taken, then the processor should assume that the next time also, the processor should predict that the next time also branch will be taken. If in the previous time the branch is not taken, then the processor should predict that the next time also the branch will not be taken. So this can be for to record this recent history. So somewhere the recent history should be recorded. So to record this recent history, we need only one bit. One bit is enough to record this history. One bit is enough to record this history. Because using one bit you can represent how many values? You can represent 0 and 1. So 0 means you can assume that the branch will not be taken. 1 means you can assume that the branch is taken. Okay, but here we are using a different terminology. That is, if branch will not be taken, then we say that LNT. LNT means likely not to be taken. Branch is likely not to be taken. If it is in the previous instruction, I mean in the previous execution, if the branch is not taken, then this bit will be set to 0, which means that branch is likely not to be taken. In the previous execution of that instruction, if the branch is taken, then this bit will be set to 1, which means LT. LT means likely to be taken. Branch is likely to be taken. So here it is there. LT represents branch is likely to be taken, and LNT represents branch is likely not to be taken. Okay, and these two states can be represented through a state diagram. These two states can be represented through a state diagram. Okay, so this represents the current state. So current state, if the current state is LNT, that is in the previous round, if the branch is not taken, then it will be in LNT. Processor will be in this state, likely that not taken. And now, so processor will predict that in the next round also branch will not be taken, because currently it is in likely not to be taken, because in the next round in the last round it was not taken. So now also the processor will assume that the branch will not be taken. But now if the branch is taken, then from LNT it will move to LT. That is, because previously it is in LNT state, now it will move to LT state, that is likely to be taken. Next time when the same branch instruction is to be executed, now the processor will assume that the branch will be taken. Okay. Now the other case, assume in the last round the branch is not taken. So now also processor assumes that the branch will not be taken, that is likely to not to be taken, and say actually now also the branch is not taken. So then it will be in the same state. It will be in the same state because branch is not taken. If branch is not taken, it will be in the same state, that is LNT. When the system is in LNT, if the branch is taken, it will move from here. This is branch is taken. This arrow represents if the branch is taken, it will move from LNT to LT. Okay. So currently the system is in LNT. That is in the last round the branch is taken. So now also it predicts that the branch is likely to be taken. So now also if the branch is taken, it has predicted the branch is taken, and actually the branch is also taken, so it will remain in the same state. So again it will be remaining in the same state, that is the next time also it will assume that the branch is likely to be taken. Okay, say the last time the branch is taken, so the processor will be in the state likely to be taken, branch likely to be taken. But in the current stage, if the branch is not taken, then from this stage it will move to this stage, that is likely not to be taken. Okay, so that's it about this particular concept. So this can be represented using a two-state algorithm, right? But let us see how this can be implemented for a for loop or a while loop. Okay, So when you want to implement this for a for loop or a while loop, say initially let us assume that, let us assume the for loop or while loop. So initially assume that the processor is in this particular state. What state? LNT, which means likely not to be taken, which means likely not to be taken. Okay, or any stage we can assume. Okay, so the processor is in this stage which is LNT, which is branch likely not to be taken. So now this instruction executes. R1 is 10. If R1 is equal to 0, out of loop. Out of loop means branch taken. Out of loop means branch taken. But processor assumes what? Likely not to be taken. So it is not taken and it will execute. Okay. So decrement R1 branch loop. Again the next round also, previously it is in LNT state. Okay. So in the next round also it will be in LNT. Because next round also R1 is what? 9. So 9 is not 0, so out of loop. So out of loop, I mean branch will not be taken, so this will execute. So like that for 10 times it will be in LNT. 10 times it will be in LNT. Okay, at last R1 becomes 0. At last R1 becomes 0. When R1 becomes 0, now also the processor will assume that the branch likely not to be taken. But now R1 is 0. So our assumption fails, the processor's prediction fails, so it will go out of loop. Out of loop. So when it goes out of loop, it will change from likely not to be taken to likely to be taken. Is it clear? It will change from likely not to be taken to likely to be taken. So currently the processor is in likely to be taken state. Okay. So the starting can be anything. Here we assumed in the case 1, we assumed the starting state is initially the processor is in LNT. But let us assume processor starts with LT state. LT means likely to be taken. So here the processor assumes that the loop is likely to be taken, but I mean the first time, but R1 is 10, so the loop will not be taken. So loop will not be taken, so the prediction is wrong. If the prediction is wrong, processor is in LT, but actually the loop is branch is not taken. So from LT it will move to LNT. From LT it will move to LNT. Okay, but for the remaining, so already one round is over. Okay, already I mean one checking is over. For the first checking, it assumed it is likely to be taken, but the assumption is wrong. It predicted likely to be taken, but it is wrong. So now it has moved to LNT. So okay, now after that remaining all 9, it will be LNT only. Okay, so totally, so after that all the 9 predictions will be correct. But anyway, at last, for the last one, when R1 becomes 0, then also the processor will predict that the branch will not be taken, but actually branch will be taken. So as the branch is taken, so from LNT it will move to LT. Okay, so why we are discussing in the sense, in both the cases the processor will finally end with LT, that is branch likely to be taken, branch likely to be taken. So now the processor is in which state? Branch likely to be taken. Okay, now assume that once again after some time this same branch is to be executed. Okay? Say after some times this same branch is to be executed. Now processor will start with which state? LT it will start. Processor will start with LT. LT means what? Likely to be taken. But because previously it ended with LT, likely to be taken, so it is starting with LT. But will it be taken? No, it will not be taken. It will go to LNT. Okay, so like that it will continue. So now the question is there any way to predict this first thing correctly? The last one is fine. The last one we cannot change anything. Okay, because we cannot change anyway. Because at last the one time the loop should fail, but we don't know which time it is. But can we make this first prediction correctly? Is it possible or not? That is the question. Yeah. So why this first prediction is going wrong in the sense, because in the previous round it will always end with LT. So the CPU processor is starting with LT. So because of that it is going wrong. So can we make sure that the first prediction does not goes wrong, or can we improve this performance is there any other way? So actually there is one method to improve, so that's what we are going to discuss next. So the next method, what it says in the sense, instead of using two states, it suggests to use four states. Now instead of using two states, the second method suggests to use four states. So now we are going to use 4 bits. Previously we used only one bit. Previously used only one bit, which represents two states. Now we are going to use 2 bits. Okay, 0 0 represents one state, 0 1 represents some other state, 1 0 represents some other state, 1 1 represents some other state. Okay, so 0 0 now will represent S and T, which means strongly not likely to be taken. Strongly not, which means the branch is strongly not likely to be taken. And 0 1 represents L and T, which means likely not to be taken. And 1 0 represents LT, which means likely to be taken. And 1 1 represents strongly likely to be taken. So now we are going to use 2 bits. With 2 bits we can manage 4 stages. So these are the 4 stages. Here you can see, if let us assume initially the processor is in say LNT, which is what, likely not to be taken. The branch is likely not to be taken in this state. So the processor will predict that the branch will not be taken. But now if the branch is taken, it will go to strongly likely to be taken state. Okay, now the processor will assume that the branch is taken. And if the branch is really taken, it will continue in the same state, strongly likely to be taken. Okay, when the processor is in strongly likely to be taken, so it is going to predict that the branch is taken. But now assume that the branch is not taken. If the branch is not taken, now also it will go to likely to be taken state. Okay, from likely to be taken state, you see here, from likely to be taken state, if the branch is taken, again it will go back to strongly likely to be taken state. So what I am trying to say in the sense, how many wrong predictions are required for the processor to move from strongly likely taken to strongly not likely to be taken? In the sense, 2 wrong predictions are required. Only after 2 wrong predictions, the processor will move from strongly likely to be taken to strongly not likely to be taken. Assume that the processor is currently in this state, strongly likely to be taken. So it predicts that the branch will be taken. But say the branch is not taken. So now it just moves to likely to be taken state. So now also the processor predicts that the branch will be taken. But say that the branch is not taken. So now the branch not taken, now it moves into strongly not likely to be taken. So when there is 2 consecutive wrong predictions from strongly likely to be taken, then only the processor will move from strongly likely to be taken to strongly not likely to be taken. Okay, right? Similarly, the reverse is also true. That is, when the processor will move from strongly not likely to be taken to strongly likely to be taken, that also it should make 2 correct predictions in a row. Then only the processor will move from strongly not likely to be taken to strongly likely to be taken. Okay, see here. Assume that the processor is currently in strongly not likely to be taken state. The processor is in this state, strongly not likely to be taken. So now the processor assumes that the branch will not be taken. But say the branch is taken. If the branch is taken, then it moves to this state, which is likely not to be taken. Now also, see, one time it is from strongly not likely to be taken, it assumed branch will not be taken, but the branch is taken. So it has moved to LNT state. But now also the processor is not assuming that the branch will be taken. No, it is still assuming that the branch will not be taken. LNT means likely not to be taken. Okay, now also if the branch is not taken, processor is assuming that the branch is not likely not to be taken. Now if the branch is taken, then it will move to strongly likely to be taken. Okay, it is here also when there are 2 wrong predictions. It is processor assumes that branch will not be taken, but 2 times consecutively if branch was taken, then it will move from SNT to ST. That is strongly not likely to be taken to strongly likely to be taken. Okay, I think it's clear. Coming to LNT state, LNT and LT are something like middle state. From LNT, processor is assuming that the branch will not be taken. If it is taken, it will go to strongly likely to be taken. If it is not taken, it will go to strongly not likely to be taken. Similarly, from LT, processor is assuming that the branch will be taken. If it is taken, it will go to strongly likely to be taken. If it is not taken, it will go to strongly not likely to be taken. Okay. So with this assumption, let us see how it is going to work with for loop. Okay, with these assumptions, let us see how it is going to work for the for loop. I mean, in the loop we discussed that always the loop will end with LT in with one bit. I mean, with two-state algorithm, it will always end with LT. So when it begins, no, what happens when it begins? It will always begin the first time. It will always predict wrongly. So can we avoid that? That is the question, right? So that can be avoided by using four-state algorithm. So that's what we are going to discuss. Okay. So initially, let us assume that the processor is in this LNT, that is likely not to be taken for a for loop. Okay, likely not to be taken. Okay, for a for loop, that is the branch occurring at the beginning, right? So likely not to be taken. So R1 is, so initially we are assuming what? Now with now we are discussing with four state algorithm. Okay, this is with four state algorithm. Four state algorithm. Okay, so previously whatever we have discussed, that is with two state algorithm. This is with two state algorithm. This is with two state algorithm. Okay, so coming to four state algorithm, let us assume that the processor initially assumes that the branch is likely not to be taken. So with that assumption we are coming. So the first instruction is R1 is set to 10, then branch R1 is equal to 0 out of loop. Is R1 is 0? No. So branch is not taken. So our assumption is correct. I mean the prediction is correct. So likely not to be taken. So from likely not to be taken, where it will go? See the diagram. Likely not to be taken. Okay, so from likely not to be taken, actually it is not taken. Actually it is not taken. So it will move to strongly not likely to be taken. It will move to which state? Strongly not likely to be taken. So now the processor is in this state, strongly not likely to be taken. Okay. Again our prediction is, again processor prediction is what? A branch will not be taken. So actually branch will not be taken. So it will go to, again it will remain in strongly not likely to be taken. So like that it will remain in strongly not likely to be taken for another 9 times. Okay, because the loop will execute for 10 times. At last time when R1 becomes 0, every time we are decrementing R1. At last when R1 becomes 0, now also the processor is predicting that the branch will not be taken. But now R1 is 0 and the branch is taken. So now what will happen to this our state, processor state? It is currently in strongly not likely to be taken and branch is actually taken. So it will just move from SNT to LNT. What is LNT? LNT is likely not to be taken. Likely not to be taken. So now it is ending with what? Now it is ending with LNT. So next time if this same loop is to be executed, it will start with LNT. When it starts with LNT, the branch will not be taken. So from LNT it will move to SNT. So we are not mispredicting anything. We are making only one misprediction, and that happens at last. At the beginning there is no misprediction. Okay. So this is applicable for any, you can start with anywhere. Instead of LNT you can also start with LT. If you start with LT, LT also, I mean first time we don't know. LT also, if you start with LT also, from LT it will move to, LT is likely to be taken, but the branch will not be taken in the first row. It will move to SNT. Okay, but finally it will end with what? Finally it will always end with LNT. As it is ending with the LNT, so next time it will only start with LNT, right? Only if you don't have any history, you have to start with something else. But based on the history, it will always, if you are recording the history, it will always end with LNT. So there is no chance for the wrongly predicting the first iteration of the for loop or any loop when it is executed for the next time. Okay, so that's it about branch prediction, and that's it about this particular topic. Okay, so with this we are finishing pipelining. Okay, let us stop here. Thank you.